Okay, so this sequence here, I have 2/5, 3/7, 4/9, a 5/11, and 6/13. And probably the simplest way of looking at this problem and building the sequence is just look at the values in the numerator. I'm just adding 1 each time on top. So my next three terms here, and let's fix those fraction bars. Let's make them a little bit longer, separate them out. Well, it's going to be 4, 5, 6, so 7, and all I'm doing is adding 1, 7, 8, and 9. I'm going to put some commas in. Let's think about the bottom numbers now. Well, on bottom in the denominator, well, 5, 7, 9, 11, 13, I'm just adding 2 each time. So let's add 15, 17, followed by 19. So here are my following fractions, my next 3 terms. 7/15, 8/17, 9/19. Cool, so this list actually goes on forever. It goes on forever, but what if I didn't want to continually build this list on fraction after fraction after fraction? What if I actually wanted to know what value is in like the, let's say, 53rd term or something? Well, in fact, I'm going to actually call that a sub 53. My index here at 53 is telling me I want to know what the value is in the 53rd term. What would my fraction be here? Well, let's see if there's a rule that we can build, some sort of generic formula that we can apply to this this entire sequence and find the 53rd term really quick. Well, that general formula, I'm going to change colors here. Alright, so starting out, my generic formula is going to be a sub n, and the index here, n, it's looking at the nth term. It could be any term. And the way I'd indicate each of these terms above, so for the first term, well, I'd actually call that a sub 1, the second term a sub 2. I'm just going to continue writing these out. A sub 3, a sub 4, a sub 5, a sub 6, a sub 7, and a sub 8. And way over here, what we're really saying is, well, what's the value in the 53rd term? So let's go on down to a sub n and look at our generic term that we're going to build. So a sub n, it's equal to, let's just ask what's happening in the numerator, what's happening in the denominator. So I'm going to go on back down here, and I'm just going to create a fraction bar because there's 2 different things happening, one on top, one on bottom. Alright, so let's look at what's happening up top. Well, to get from the one term to the next, I'm always adding 1, I'm adding 1, I'm adding 1. So maybe it's something along the lines of I'm adding 1 to the previous number. But how do I plug a previous number in here? Well, I'm going to think about it as let's plug a variable in. And the only variable I really have to play with right now is n. So this value n, I'm going to go ahead and plug it in right here. So n plus 1, and I'm actually going to go and play around with this first term here. I'm going to take a sub 1 and write it below, and let's just build that at the same time to see if the generic formula that I'm creating here is actually going to be useful when actually running through the sequence. So for a sub 1, we're saying when n is 1, when my index is 1, so for a sub 1, notice here, I plugged a 1 in, I substituted a 1 in for n. The reason I did that is because this is my first term, and I'm labeling my first term with a sub 1. So whenever I see an n, I'm going to plug a 1 or substitute a 1 in that spot. I see an n in the numerator as well, so I'm going to substitute a 1 in right here in the numerator, and I'm going to just add on whatever's left in that formula. So 1 plus 1, I'm going to fix that last one. So 1 plus 1, well, that will give me a value of 2 in the numerator. So let's see if this checks out. Well, in the numerator in the first term I have a 2, so this is checking out. What I want to do from here is actually build another one. Let's say a sub 4. What happens when I'm looking at the fourth term here? So let's see here, I'm going to substitute 4 in for n. So I'm going to substitute a 4 in here. We're going to add 1 to it, and 4 plus 1 will give me a value of 5. So let's see if there's a 5 in the numerator for the fourth term. There is. So it seems like this formula, this generic formula, is holding true at least for the numerator, and it was really easy to build. Let's see if it's that simple for the denominator. So notice the change in the numerator was adding 1 each time, and all I had to write was n plus 1. The change in the denominator, it's changing by 2. I'm adding 2 each time. So can I just write n plus 2? Let's try that out. n plus 2. n plus 2. So that means I'm going to take the value for n and substitute it in for n here. So So in this first term, I'd take 1 and substitute it in for n, and then add 2 to it. So 1 plus 2 is equal to 3. Is there a 3 in the denominator here? No. So this actually doesn't check out. It looks like it's not going to be that simple. So I've got to find some other rule that's going to work here. How can I build that? Well, I'm going to go back to that difference, but I need to change colors first. What was the difference between 7 and 5? Well, we said 2. The difference between 9 and 7 is 2. The difference between 11 and 9 is 2. So I always have a common difference of 2. So I can see that my common difference, it's 2. So I know that 2 is going to play a part in this denominator. I'm going to put a 2 down here. And way over here to the side, I'm going to build a little table. This is what I do with my 6th graders here. We build a little T-chart. And this first value is for my term. You could think of this as an X value if you wanted. It really doesn't matter. And the second one is my actual value for that term. And you could think of this as like a Y value, or another way of thinking about this is your input, which means that over here you'd have your output. Or really, again, like I said, it doesn't matter as long as you are plugging in the correct information. So we have different ways of looking at it, and I'm going to think about it as my term and my value here. So for my first term, second term, third term, fourth term, and fifth term, what values do I have? My first term is 5, so we have 5, 7, 9, 11, and 13. Okay, so from here I'm just going to change colors because there's a lot of blue there. And I said the common difference between each of these terms is 2. It's 2. It's changing by 2 each time. So it's changing by 2. So what I can do from here, since it looks like an arithmetic sequence, I'm always adding 2. So a trick with an arithmetic sequence is just wrap it around to the other side and multiply your common difference by the term. So this would be 2 times 1 in this case, so I'm just going to put a multiplication symbol here. It's going to be 2 times the number. So 2 times this value is 2. How do I get from 2? The next thing I'm going to say is, how do I get from 2 over to 5? How did I get from 2 to 5? Well, I had to add 3. I had to add 3 after that. So let's see if this method actually holds true for the rest of this sequence. So if I were to take 2 and multiply it by the next number in the list, which is 2, well, I'd get 4. How do I get from 4 to 7? I have to add 3. If I were to do that again and multiply 2 times 3, well, 2 times 3 is 6. And how do I get from 6 over to 9? I have to add 3 to 6. So then let's fix that addition symbol there. So this, plus 3, 6 plus 3 is 9. So it looks like this method's holding true. Just multiply 2 times your term that you're looking at, and then add 3. So then add 3 to it, and you'll get the value of that term. So what I'm seeing here is I'm going to take 2, I'm going to multiply it by the term value, which in this case, the term value, we're going to call it n. So 2 times n, and then at the end, at the very end of all that, I'm going to add 3. So 2n plus 3. Okay, so then what I'm going to actually do is apply this method to these two problems below. We've already done the work over here. I already know it works, but I'm just going to plug it in so we can visualize it here. All right, so now, all right, so over here I have 2 times 1 because I have a sub 1. My value for n right now is 1. So 2 times 1 plus 3 in this case, plus 3. So 2 times 1 is 2, plus 3 will give a value of 5. All right, and this actually checks out. We've already done that work and proven it, but now let's just do it over here. 2 times 4 in this case. 2 times 4 plus 3. 2 times 4 is 8, plus 3 is 11. So 5/11ths, and that actually checks out. And now we could actually apply it to a sub 53, our 53rd term here, and let's see what we get. All right, and let's apply that here. A sub 53 is equal to, so we have 53 plus 1 on top, and then on bottom I have 2 times 53 plus 3. So I have a sub 53 is equal to, Well, 53 plus 1 will give me 54 in the numerator. So 2 times 53, that's 106. So 106 plus 3, 106 plus 3 is 109. So A sub 53 is equal to 54 over 109. And I can box that up. Now this didn't actually answer the problem. Cool, now this problem wasn't actually asking for the value in the 53rd term. Remember, this problem we were just really specifically looking for the next 3 terms in the sequence, the next 3 terms, and we answered that way earlier. Alright, I'll see y'all in another video.